Hi everyone. Today what we're going to work our way through is dealing with graphing reciprocal trig functions. And so where you want to be as you walk in today is going to be that you are comfortable to be able to work your way through graphing any of your basic reciprocal curves. So you are solid at graphing your cosecant, secant, and cotangent graphs. If we have that in our background, then today what we're going to do is we're going to deal with graphing those functions, dealing with transformations. So when you take a look at the graph in A, you notice that we have our secant graph. What I'm going to recommend for you to do, just for this one, is to go ahead and put on your basic secant graph. So pause the video, take a moment, and put on a graph of your base secant curve. Okay, pause the video now. Okay, and we should be back. So we know that our secant graph is the reciprocal of cos. Cos starts at 1 and falls. So if we have a maximum at 1, then that means we have a minimum on our secant. We hit 0 at pi by 2, so the reciprocal of that would then be our asymptote. Then we go through and we hit a minimum at -1, so that becomes a max. We come back up and hit a 0 at 3 pi by 2, so that becomes an asymptote. And we then hit our max, so there is our min. So if I was just to put on that secant curve, then as I'm getting down my branches, we would get something like that. There is our base secant curve. Now, my suggestion to you is if you like putting down your base curve, because then that gives you the ability to go through and transform it well, no problem with doing that. Two things. Number one, make sure you label that graph, because that means you will have multiple curves on your set of axes. The second suggestion I would give, don't put on your asymptotes. And so you'll notice me erasing my asymptotes, because what happens from time to time is as we begin dealing with all of these curves, you start seeing multiple asymptotes on your graph. It can be really confusing, and it can cause you to actually connect and use nature of the curve incorrectly. So if you like to put on your base curve, then I would suggest only showing what you see in green. You know where those asymptotes exist, but we don't have to put them down. Okay, now that we have that green curve, now what we're going to do is we're going to deal with those as transformations. So I'm going to do this using some intermediate graphs. And so the first thing that I may examine is me going through and dealing with the -3 as a coefficient. I know the negative means I'm going to reflect it in the x-axis, and I know that the 3 means that I need to have a vertical stretch by a factor of 3. So this first point that I've just put as an x is then going to get reflected across the x-axis and vertically stretched by a factor of 3. So it's going to get stretched down to 3. There is its finishing position. So I should be good to just get rid of all of that red. I'll clean up that green really quickly. And there is that first point transformed. We then know that that branch is going to get steep because it had a vertical stretch by a factor of 3. And so we're going to see something like that. I can do that same thing with all my branches. So on that middle branch, I'm going to reflect it, vertically stretch it by a factor of 3, and that's where this maximum becomes a minimum. And do the same thing at the end. Reflect across the x-axis, then vertically stretch, and make it steep. So if I come up with that red curve, then that is me, and I'm just going to go through and fix up that green graph. Then that's the only portion I see. Now, what's important for us is we may feel like we goofed up because like we only see a little bit of the function. But keep in mind that between 0 and 2 pi, and on our y-axis, looking and just saying that all I can see is up to 3.5 and down to negative 3.5, then it's possible that within that window, there is only a small portion of what I can see on my graph. If I vertically stretch by a factor of 3, then my window, or that gap that I had between my max and my min branches, is also going to get stretched. So this kind of acts like your amplitude. That if you notice the height of this purple on my original graph would be a height of 2 units, you know your amplitude is half the height. That if I was then to take a look at the red is going to go all the way from 3 down to negative 3, then we should have a big gap in the middle of that curve. Okay, I'm just going to get rid of all of that mess on that side because, of course, we would never put that. But it's important for us to note, especially on this first graph that we're producing. Okay, if I am going to use intermediate graphs, then I've got to label them. So what that red graph is just the graph of negative 3 secant x. Well, I think we can now produce our final graph because now we can incorporate the 2. That 2 is going to be a horizontal stretch by a factor of a half. So now I need to take all of that and I need to make it half the distance to my y-axis. So that's not going to change this point that's on my y-axis. However, that branch is going to become even steeper. The asymptote at pi by 2 that was not affected by the vertical stretch or the reflection in the x-axis is now going to get stretched 1/2 the horizontal distance, which means it used to exist at pi by 2, it's now going to exist at pi by 4. So I then have, man, is that a really sloppy asymptote? I now have that asymptote that exists at pi by 4. Okay, that minimum way up on top of my graph that exists at pi is then going to exist at pi by 2, half the distance, and I get a steep branch. My next asymptote that would have existed at 3 pi by 2 has to be half that distance, so 3 pi by 4. So I then have that asymptote. My maximum that occurred down at 2 pi is now going to be half that distance, pi, with a big branch. And what you see then in blue would be the shape of my final curve. Now my only job, take that, and since it's a periodic function, stamp it to fill in the complete graph. And so I would then have the rest of this branch. I notice that every pi by 2 units, I'm going to have an asymptote. So 1, 2, 3 grid lines would be pi by 2 on this scale. That then means that halfway between another 1, 2, 3 pi by 2 would create another asymptote. And halfway in between, I'm then going to have this minimum up top. And then halfway. And finally, what I have then with that blue graph is the graph that I was asked to graph at the very beginning. So That, I think, would be as long and drawn out of a process as what we would encounter. We use some intermediate graphs. We graph the base function to begin with. If I was to give you a question like this on an evaluation, the only thing I would ever have to see is the blue curve, the given graph. Feel free to use intermediate graphs, but I want to kind of push us away from using them. So let's see where we can go with this stuff. So you take a peek and you notice that I've actually given you a primary curve in this instance. Remember that you'll be responsible for going through and graphing a tan curve. Tan is the new primary graph for us. So for us to be able to go through, we still need to be able to graph our tan curve. So the first thing I may think of then is, well, what is my base tan graph? And maybe we're still at that point where we go like, yeah, but I'd like to be able to put down my primary curve. So let's put down the base curve. So I know that my tan curve starts at 0 and then does that wavy thing. I'm going to fight the urge, there's my pi by 4 by 1, to put on my asymptote, because then those walls just get way too complex. I know that I have my next 0, a pi by 4 on either side of that gives me my 1s, and that's what creates the shape of my curve. And so I can deal with that same thing down at the end. And without putting in my asymptotes, I have a pretty decent tan curve. Okay, what I'd like you to do now is pause the video. Let's go through, because I think that you should be able to graph the transformed version of that tan curve. So pause the video now, give it a shot. Okay, we should be back. So what I'm going to do is I'm going to jump over all the intermediate stuff. And instead what we're going to do is we're going to walk through each one of these transformations going to our final curve. Now, I'm going to do a bunch of stuff in colors to maybe help out. So we're going to deal with the vertical stretch by a factor of 2 in blue. We're going to deal with the shift right pi by 4 in red. And we're going to shift down 1 in gold or yellow. That's going to finish off with a purple curve in the end. Okay, if I were you and I was going to go through and deal with all this stuff, then what I often find easiest to transform first are my asymptotes. So I'm going to do all those transformations to the first asymptote on that green curve, that being at pi by 2. So I know pi by 2 gives me an asymptote. If I vertically stretch that, then that's going to have no effect on that vertical line. When I shift it to the right pi by 4, then I need to shift it that pi by 6 and another bit. So there's my pi by 4. Then I go through and I shift it down 1. Well, shifting it down 1 isn't going to have any effect. That I know the finishing position of that asymptote is going to be right there. I can get rid of that red then. We're now at our finishing position. Okay, I'm going to do the same thing with my other asymptote. Now I notice it's a vertical line, so none of the vertical transformations are going to affect that. The only thing that's going to affect it is the shift right pi by 4. And so my other asymptote on my tan curve was at 3 pi by 2. Shift it to the right pi by 4. There is now my finishing position. And of course, you're going to use a straight edge as you do this. There is your asymptote. Same thing, I can get rid of my red, and I am good. Okay, now I've got my walls that I know that my curve is not going to cross. Now I'm going to start to transform my points. I think the next thing that I would deal with is transforming my zeros. It's nice because my vertical stretch will have no effect. So I'm going to take my 0, my first one that exists at 0. Vertical stretch by a factor of 2 has no effect. Shift it to the right pi by 4 and down 1 unit. Remember, 1 unit, not 1 grid line. So there is the finishing position of my curve. And now I can do the same thing to all my zeros. So my next 0, which did occur at pi, shift it to the right pi by 4, down 1, there's my finishing position. You'll notice my last 0 is going to get transformed off my grid because of my shift right. So I do not graph it. I can then get rid of all these red and gold arrows. And there we go. Okay, we're starting to build our curve. The last thing that I want to go through and deal with now are my 1s. Okay, my 1s are going to get affected by every transformation. But I'm also going to use symmetry to help me out. So let's walk through the first one. That first 0 that occurs at pi, that first 1 that occurs at pi by 4. If I vertically stretch that by a factor of 2, then it's going to transform that up to a y value of 2. I then shift it to the right, pi by 4, and down 1 unit. There is the finish of that point. So I'm just going to get rid of all those arrows again, but I also want us to be able to maybe take a look at some things that I can use to help me through that process. I'm just doing my best to not erase too much on that curve for speed's sake. Okay, I want to put something else on here because you'll notice a relationship that I can use as a check. That if I was to examine my base tan curve, I know that I am over pi by 4 and I am up 1 unit. My normal tan curve has a leading coefficient of 1. It hasn't been vertically stretched. So over pi by 4, up 1. I'll notice that this tan curve is over pi by 4 and up 2 units. It gives me a little bit confirmation. And so I feel like I've done a pretty good job then being able to go through and graph that, at least with respect to my horizontal shift and my vertical stretch. So I can right now pretty confidently curve up and approach my asymptote and get that portion of my curve. Now, if I am very confident with that action, then I know that that curvature has to be repeated because of the periodic nature of your tan curve, which means I could go over to the next 0 and do the same thing. Go to the right pi by 4 and go up 2 units. Connect those curving up, approach the asymptote, and we get the same thing. Notice, more importantly, to get the rest of the curve, my curve is symmetrical, which means if I went back pi by 4, I would have to go down 2 units. I know that I'm also passing through that point. And so now when I'm curving down, I would get that portion of my tan curve, which can be repeated right pi by 4 down 2. Notice I didn't put an arrow on that end. Because I'm graphing from 0 to 2 pi, I'm not going to have an arrow on the end of that function or at that position at 0. Okay, I'm just going to get rid of all those red little arrows to clean up my graph. And we may be tempted to then go, oh, okay, I'm done. Walk away onto the next problem. However, take a look at the end of that grid and you'll notice that we have a small portion of x values that have not been graphed. This little interval at the end has nothing existing in it. And as we discussed before, perhaps nothing should exist in it. However, we do have to check. And so what I'm going to do is I'm going to do a quick check on my period. I know that the period on my normal tan graph is pi units. And nothing that we've done in this function would change that period. Notice there is no horizontal stretch. So my period for this tan curve should still be pi. And on an interval that goes from 0 up to 2 pi means I should have 2 complete cycles. And so since my curve started down at this, I should have the exact same pattern repeating twice, which means that point is going to exist on my graph. And we're going to see this small little portion of that branch exist. You give me the purple curve and you guys have got a great sketch, a great graph of your tan curve. Okay, let's jump back into some reciprocal stuff now. And so as you take a look at the function given in C, you'll notice that we have our cotangent function. And so we're probably feeling the least confidence when it comes to cotangent, just similar to, dealing with our tan curve relative to our sine or our cos. So we may still want to go and put on our base cotangent graph to be able to then transform. So if we go through and we relate everything from our cotangent graph back to its primary curve, our tan curve, well, we know that we have our tan curve starts at the origin at 0, which means its reciprocal would give us an asymptote. So I know that I have an asymptote at an x value of 0. We could then work our way across. Your tan curve has another 0 at pi. That asymptote I can put on. And at 2 pi. So as we have our asymptotes at 0 pi and 2 pi, that's where we're picturing our decreasing wavy curve falling in between all of those asymptotes. If you recall though, let's not put asymptotes down, but let's instead put down what that curve looks like. So in between those asymptotes, I'm going to hit my 0. I know that a pi by 4 on either side is going to give me my 1s. And so then I could sketch my curving up, now curving down. There is my cotangent, or one cycle of my cotangent curve. I know that my next 0 could exist, pi by 4 on either side, and the same thing. There is my base curve, and now I can go through and deal with those transformations. So we notice that we're going to have a reflection in the x-axis. We notice that we're going to have a vertical stretch by a factor of 3, which is going to make that graph a lot steeper. And we then notice that we need to shift our curve to the left pi by 3. So what I'd like everybody to do is just pause the video and go through and produce a transformation of that green curve, your cotangent curve, with those transformations. So pause the video now. Okay, and we should be back. So in this instance then, I'm going to go through and just deal with what I did on the previous graph. So if I begin with my zeros, because those are the easiest things to deal with in this instance, I notice that that reflection is not going to have any effect. That vertical stretch is not going to have any effect, but I will be able to shift my zeros to the right pi by 3. And so on my scale, pi by 3 would be 2 grid lines. So if I move that 0 to the right, that gets me to that finishing position. And if I move that 0 to the right, that gets me to that finishing position. Now, the other issue, and I don't want us to ever forget it, is that even though I haven't graphed my asymptotes, I still like to transform them early. So I'm going to picture that asymptote that would exist at 0. And I notice that my reflection is not going to have an effect, my vertical stretch is not going to have an effect, but this shift left will. And as I shift left, I'm going to notice that that asymptote is not going to be on my grid. So I'm not concerned with then graphing that. In fact, I am not going to graph that. So the next asymptote that I'm then going to focus in on would be the asymptote that would exist at pi. So we can pick up the pace a little bit. The reflection, the stretch aren't going to have any effect, but when I shift that to the left, pi by 3, I then know that I'm going to have my asymptote at 2 pi by 3. Now I can do that same thing and shift my asymptote that would exist at 2 pi. And that got a little sloppy. To my 5 pi by 3. Okay, I've got my asymptotes up that are going to act like walls. I have my zeros up, and those fall directly in between. I'm feeling pretty confident. Now I need to transform my 1s to make sure that I get my curve the correct shape. Okay, first thing I'm going to focus in on then is going to be this one that exists right here. I want to focus in on that -1 point that exists at 3 pi by 4 because I'm not going to focus in on this point because I know that this shift is going to move that point off the grid. Okay, I'm just going to get rid of all that yellow. So I'm going to focus in on my 3 pi by 4. So first thing I can do is I can reflect that in the x-axis. So it is then going to lie at this position. I can then vertically stretch it by a factor of 3. So instead of being at a y value of 1, it is going to go up to a y value of 3. And now I can go ahead and I can shift that 2 grid lines, so pi by 3 units, and there is my finishing position of that point. Okay, I'm just going to get rid of some of that detail, and we can get rid of the blue, the red, and the gold. We see how we arrive at that finishing position, and we should be good. So at the very least, I know that my curve is going to become steep and look something like that. Okay, now let's get the next cycle. So I know then that I'm going to take this point that would have existed at 1 and do the same transformations. So let's reflect it across the x-axis. Let's vertically stretch it down by a factor of 3. And now let's shift it to the left, pi by 3. We get to that as our finishing position for that transformation. Again, I can get rid of all these extra little marks. And I can do the same thing with my next point. Now, depending on comfort level, if we are really confident that this point that I just transformed was accurate, then I'm going to use the fact that my cotangent curve is symmetrical around its zeros to get my other one. I can tell that if I went pi by 4, I would then go down 1, 2, 3 units. That if I am symmetrical, then I have to be pi by 4 and up 3 units. So I'm just going to get rid of all of that red and then be able to work my way through to say that I know I have a matching point that lies here. So I can now connect them with that wavy thing that we know our shape is. The fact that it starts to be stretched to the point where we start to lose the appearance of the curvature. That's a good thing. As we are vertically stretched, we're going to see less of that curvature, and that curve is going to look more and more like a line. That if we got down to that point, I think we're doing great. Okay. But we notice that we're missing some parts. Okay, I want to come in on this detail right in here. What's happening in between those values? We clearly can tell that this curve is going to come down. However, does it leave our curve here, or sorry, our grid here? Should it leave it here? We're going to need to be accurate as we go through to now begin that graph. So, there is nothing wrong with, in this instance, to make sure that we are accurate, we're going to now sub in an x value of 0 to find our y-intercept. And so with a pretty quick calculation, we can go through. Now we can do a little bit of calculation. I'm only looking for an approximate, so we don't mind if you're pushing buttons on this. However, we should be pretty comfortable to then say that if I need to calculate the cotangent of pi by 3 is going to be here. That's a root 3, a 1, and a 2. Cotangent would then be adjacent over opposite. And so we could go ahead, and yes, you could rationalize that, get that exact, but really what we need is an idea of where we should leave that grid. So I now know that at approximately negative 1.73, so negative 1, 1.5, and about halfway through, that's a pretty good estimate then of where our graph should begin. We come back to what we discussed in the last graph. I notice that I have this last interval with no part of that graph in there. I notice that my period for my cotangent should be pi. There's been no horizontal stretch, which means I'm going to have exactly 2 cycles exist on this grid. And so if I start at that value, then I need to end at that value. So way down here at 2 pi, I should have the same value, and we should be able to see that portion of our wavy thing, of our curve. Okay, there's your cotangent graph. Now let's move on to our last one. Okay, and so you're taking a look at the equation for the function given, and you notice it's a cosecant graph. So we have in our mind the idea of what a cosecant graph looks like. Now we're going through and we're trying to interpret all those transformations, and I know that no one is going to get caught off guard by the fact that you do not have a coefficient of 1 on your x. That we need to factor out that 1/2. And so, as we work our way through on that, when we factor out, remember, or I gave a little reminder a few lessons ago, that when we get into factoring out that 1/2, there could be a very common mistake here. So instead, go the other direction and say, well, what would I multiply 1/2 by that would get me back to 1/3? And hopefully we can come in on the 2 pi by 3. Little confirmation that when you pull that factor out, or if you re-expand, we notice we get back to the original. So we can now interpret our transformations. We see that we have a vertical stretch by a factor of 2, so our graph's going to become steeper. We notice that we have a horizontal stretch by a factor of 1/2, so our graph is going to become, a horizontal stretch by a factor of 2, so our graph is going to become flatter. So those two stretches are going to battle each other. And lastly, we need to shift our curve to the right 2 pi by 3. So now that we have all those transformations, what I would love for you to try is, can you go directly to your final curve? So that is, don't go and put on what your cosecant graph looks like and then transform it. Rather, think about what your cosecant graph would look like and perform the transformations to it. So I'd love for you to try. Feeling brave, give it a shot. If we're not so, right now, comfortable with it, then maybe we do put on our base cosecant graph. I'm going to go start to finish, and we'll see if we match up in the end. So pause the video now. Okay, we're back. So the very first thing that I'm going to always do when I take a look at my cosecant graph is I know that that is the reciprocal of sine, and so I'm going to use sine to build it. I know sine starts in the middle, so it starts at 0, therefore its reciprocal would have an asymptote. So I'm going to take the asymptote that would exist at x equals 0, and I'm going to perform those transformations to it. My vertical stretch would do nothing. My horizontal stretch would do nothing. The only transformation that's going to affect that is going to be my horizontal shift, and so that asymptote is then going to get shifted over to pi by 3. That phase shift is to the right. Okay, the next thing I consider is where my next asymptote would be. So I know that my sine curve rises and falls and comes back to 0 at pi. Well, now that means that would be the next asymptote on my cosecant graph. But very quickly I can see, because of that stretch, that asymptote at pi is going to get stretched out to an asymptote at 2 pi, that then once I shift it to the right, I'm shifting it off my grid. So that will be, what you see in purple, the only asymptote that we see on this curve. Okay, I don't have any zeros on a cosecant, but I do have maxes and mins. So I think back to my sine curve. My sine curve hits its max at pi by 2, so that becomes my min. That means that I'm going to go through and I'm going to transform this minimum on my sine curve. On my cosecant graph. Okay, I need to vertically stretch that by a factor of 2, is going to put that up to that position. I then need to horizontally stretch that by a factor of 2. So that means it's going to double its distance from the y-axis, so out to pi. And then I need to shift it to the right, pi by 3, 2 pi by 3. There is my finishing position of that point. Okay, I'm just going to get rid of all those details. Pause the video if you need to. But I know that that point represents a minimum. Okay, I start to look at the rest of those features and I say, well, I know that I would have a local max that would occur out here, but clearly as soon as I do my horizontal stretch, that is going to get stretched way off the grid. Okay, well then that purple point that we dealt with is the only key point that we have on our graph. Okay, so how do we have then a relatively accurate picture? Okay, well, the next thing I might do is I might say, what's going on in this interval? So the first thing I might do then is I might find my y-intercept. So to find my y-intercept, I can sub in x equals 0. And when I sub in that 0, it's going to wipe it out, so I have a negative pi by 3. Now I can deal with my picture, and I know negative pi by 3 puts me down here. I almost don't even have to label that diagram anymore. We're pretty solid with it. We know that cosecant would be hypotenuse over opposite. And so then if I went to calculate that, I need to calculate a negative 4 divided by root 3, and that's going to get me about negative 2.31. So I know then my y-intercept would have to be somewhere close to there. Now I know that that's not a maximum. It's just a y-intercept. But I really do have enough on my curve right now to be able to make this graph pretty representative. I do know that I'm going to have my branch that comes down here. I do know that my curve is going to have to approach my asymptote, so I've got somewhat symmetrical sort of appearance. But now I run into the same issue at the end of my interval, at 2 pi. Okay, I could go through and say, I'm going to sub x equals 2 pi into that curve and do the same thing. But just like our tan and cotangent, I'd hope we'd stop for 1 second. We take a look at what the period is for our curve, and we know that the period for a normal cosecant graph is 2 pi. Now, because we had a horizontal stretch by a factor of 1/2, we know that our new period is going to be 4 pi. Well, since we're only graphing 0 to 2 pi, I can't even fit on one full picture, a full cycle. However, I do know that because I'm graphing from 0 to 2 pi, that's half of my period, that I should get half the picture. And if we've been comfortable with our cosecant graph enough, then we know that those branches are somewhat symmetrical. They have the same shape. And therefore, when I found out that I was starting at negative 2.31, I actually found out that I was finishing at positive 2.31. By doing this, I get a half of a period on my grid, which matches. Of course, you could always go through and sub in x equals 2 pi and solve to be able to come up with that end value. Okay, throwing a lot of stuff at you for today. But there is us graphing our reciprocal functions. So your job now, jump in, play around with some practice, get comfortable with it. What you're going to notice on Wednesday or the next slotted time, it's basically a work period. So what I wanted to do was allot another period of time for you to be able to play around with these problems and get a lot more comfortable with it. Okay, get some practice. Best of luck.